So, greetings to all of you listening to this video. This is your course instructor, Khushwant Fatnani. Let us start off the class where we'll be discussing today solutions to the assignment of gravitation. Let us start off. But before we begin, let us have a quick prayer. So, all of you, please join your hands, close your eyes. Let us meditate. Eyes are closed, one by one, 3 deep breaths. Smile on the face. Count 1. Breathe in and breathe out. Count 2. Breathe in and breathe out. Count 3. Breathe in once more and breathe out. Now, let us pray. Eyes are closed. Smile on the face. With all the conviction, goodwill, and right intention, let us pray to the heavens above. Dear God, we are your children. We thank you for all the love, for the blessings, and your kindness. Thank you for this life and all the gifts of life. Thank you for all the support, motivation, and love received from our family, support of our parents, friends, and guidance from the mentors. Thank you for your favor on my health, education, career, finances, and my family. I thank you in advance. Dear God, I thank you in advance that I have cleared JEE Advanced 2020 in flying colors. Dear God, I thank you in advance for clearing NEET 2020, NEET 2021 in flying colors. Thank you that I've got the admission into. Thank you that I've got admission into one of the best college of my dreams. Thank you in advance for getting admitted into the college of my dreams. The dream given by you. Thank you, thank you, thank you. With smile on your face, let us open our eyes and our hearts. Let's start. So we are taking discussion of questions from gravitation assignment, right? All right. So, like always, let us all be responsive. Thank you very much for your presence. Let us start. So, I would want one of you to start with. Let us take Fire. Fire, can you please for us read the first question? Yes, Fire.
Okay. Okay, sir. A rod of length L and mass m is bent to form a semicircle.
Mm-hmm.
What is the gravitational potential at the center of the circle?
Okay. So we have a rod, right? We have bent the rod so that it can form a semicircle, and the length of this rod is L. Let's say its radius is R. We are being told if this is the center O, at this center, what is the gravitational potential? Gravitational potential. So we'll recall about the concept of gravitational potential. Gravitational potential is nothing but potential energy or gravitational potential energy per unit mass. So we had read that gravitational potential energy is minus gmm by r. R is the distance between that mass, the two masses which we are talking about, and this is the mass of the body for which gravitational potential is being calculated. So we'll have minus gm by r, where this m is basically the source body due to which the potential is being calculated. All right, Fayed, any idea of the approach that we should adopt in order to solve this question? So we are being told, class, to find out the gravitational potential because of this bent rod at the center of this semicircle. Yes, Fayed.
We know the potential due to a ring is given by minus Gm by R.
Mhm.
So the same formula we can use for this also, right?
See, so how will we solve this question? Do you remember that question, Fayed, which we had taken yesterday, where we had continuous distribution of mass along the length of a rod, and we had to find out what is the force acting on a small mass m, which is kept at the origin.
Actually, I wasn't there
Okay,
yesterday. I was in.
okay, no worries. So basically, I'd taken a question. No worries. You can just log in onto my channel, Physics with Fatnani, and have a look on that question. So in such questions, Fayed, what we do is we take a small element, right?
Yeah,
We take a
Dm.
small
Okay.
element and we try to find out, let's say the element is dm. We try to find out what is the value of the potential or elementary potential dv at this point. Once we get that, then we integrate that
Yeah. Okay.
value
Okay.
for the entire length of the, or for the entire uh, structure, in this case length of the rod. Is the approach
Mm.
clear? Right?
Yes. Yes.
So
Yes,
if
sir.
so if for mass m, if for mass m, a point mass m at a distance r, the potential is equal to gm minus gm by r. So minus gm by r, right? So how about the potential? How about the potential dv because of a mass dm? So let's say this is the mass dm, right? We're talking about,
Okay.
and because of
Yeah.
this, here we have to find out what is dv. Yeah, tell me. By the
Okay.
same
So
analogy, it should be,
we can use Dm as m by L into R d theta.
yeah, and we should, or maybe we can first write minus g into dm by r, right?
Yeah. Yeah.
Right now, what we can do is the total potential v is nothing but integral of dv, correct?
Yeah.
Which is integral of minus g dm by r. What is
Mm.
this r? This r is the distance between this dm, this
Yeah.
mass, and this point O,
Constant.
right? Now this distance along the length of the entire semicircle is constant because it's the radius of the semicircle. It does not
Mm.
change whether I talk about point A or I talk about point B. This r remains the same, right?
Yeah.
So since it's a constant, r is a constant, and so is g, I can bring them
Yeah.
out of the integral sign, correct?
Yeah. Yeah.
So we'll have r, just a second. So we have r as well as g both coming out of the integral gives us minus g by r integral dm, right? Let us take this from 0 to total mass is, let's say, m, right? So therefore we get this as minus g into m by the radius r. Am I correct? Where r and r are the same,
Okay.
right? Am I clear?
Yeah, okay. Yes, sir.
All right. Now, but in the question we have been given with the length L. Now I know what is the perimeter of a semicircle. It is equal to pi into r, right?
Pi r.
So pi r, or the length, is nothing but the length of the rod. So length of the rod therefore becomes equals to L. Pi r is L, which implies r is equal to L by pi. Correct? Right? So this gives me L by pi, and therefore my answer comes out to be V is equal to minus V is equal to minus pi
Gm pi
Gm
by
by
L.
L. Right?
Yes, sir.
Am I correct, Fayed? Is the entire approach clear to you?
Yes, sir.
All right. Can you just repeat it in one or two lines for the entire class? Yes. Yes, Fayed. Go ahead.
Okay, so first we go to the basic formula dv equal to minus gdm by r,
Right.
and from there we know that g and r are constant, so we
Right.
take them out of the integral.
Correct.
We integrate dm, so that comes out to be m, capital M,
Uh-huh. Uh-huh. Correct.
and then we relate radius with the length L using
Right.
the perimeter formula.
Absolutely. So this is how we get the answer, that the potential due to the entire semicircle is minus gm upon L by pi, right? Or we can write this as minus pi gm by L, right? So class, if
Yes, sir.
this approach is clear to all of you, please raise your hands. Yes. Okay. Karuna, any queries? Yes, you may ask, Karuna. Yes, Karuna, you can ask if there are any queries. Yes, Karuna, go ahead. Okay, you're clear. Okay then. Right, so class, let's move to the next question. We'll take Siddharth this time. So,
Yes, sir.
all right. So, Siddharth, can you please read the question for all of us? Yeah.
Sure. 1 second. So the second question is, find the depth at which value of acceleration due to gravity becomes 1 by n times the value at the surface.
All right. So, the question says that let's say at the surface of a planet, acceleration due to gravity is g. We need to find out if this is the center of the circle, that what will be the depth at which the acceleration due to gravity becomes 1 by n times. What will be the depth? So let's say the depth is d, and at this depth, the new value, that is g dash, new value for acceleration due to gravity is g by
G
n,
by n.
and this is the radius of the planet. Okay. So any
Yes, sir.
approaches for any approach for this question, Siddharth?
Just 1 second, sir. I'm allowed to look at the formula sheet, right?
Yeah, sure. Please do.
Um, so, so we have acceleration due to gravity on surface and at height h. So can we take a negative h? I mean, negative height.
No, we have a different formula for it. Have a look.
Um,
See, so we have a formula which connects the height, the depth,
oh, at depth of surface below
right?
the Earth.
Right. So there is a formula which connects the acceleration due to gravity at a given depth d, right?
Yes,
So
sir.
correct me, Siddharth, if I'm wrong. G is, and I
G
hope
s times
is equal to g times of, that is g at the surface times of 1 minus
1 minus d by
d
r.
by r, right? Is this the
Yes,
formula?
sir. Yes, sir.
Right. So this formula is actually telling you that what will be the depth. So instead of g dash, we can also write gt, or the value of
Yes, sir.
acceleration due to gravity at some depth from the surface. And that value is given by gd, right?
GD. Yes, sir.
Now that is equal to 1 minus d by r. We are being told what is the value of d. This is the question when this g at the given depth is given by g by n.
G by n.
Right. So how will we go about it, Siddharth? Just let me
So
know.
first off, directly substitute and simplify as far as we can.
Uh-huh.
So we cancel that g on both sides, and then we get 1 by n equals 1 minus d by r.
Right. After which it is a simple play of algebra, right? So we'll
Yes, sir.
take g from both sides, with this giving us 1 by n is equal to 1 minus d by r.
We can take the LCM on that side and bring r to this side.
Yes. So we need to
On the
find out
RHS and
d.
bring r to the left side.
We have d by r is equal to 1 minus 1 by n, and therefore this depth is equal to r times of 1 minus 1 by, right?
1 by n.
Very
Yes, sir.
simple, right? So class, so first of all, Siddharth, are you clear with this
Yes, sir.
strategy? Easy,
Yeah.
but it's important that you remember this formula, right, Siddharth?
Yes, sir.
All
Yeah.
right. So class, in case this is clear to all of you, please raise your hands. Yes. Great. So let's move to the next question. Siddharth, in case you can be in this question too, we'll take it up. Yeah.
Sure.
So
So
can you
this is the
read the
question 3
question?
now.
Yeah. Can you read the question?
Yes, sir. An asteroid of mass m is approaching the Earth.
Uh-huh.
Initially, it is at a distance of 10 RE. So what is this unit over here? Initially, it is at a distance of 10 RE, it says.
So Ari, just look at the end of the question. It's given that Ari is the radius.
Oh, radius of the Earth. Okay. Right. So it initially it's at a distance of 10 times the naught. Sorry. It hits the Earth with speed v given as, and then the four options are the first one is
So
square root of 2 gm by me times r
uh-huh. So we have an asteroid here. Just give me a second,
times 1
class.
minus 1
Just
tenth. Then the
yeah,
second one is yes,
just
sir.
1 second. Just 1 second. Sir. I think there is some issue with my network connection. Just a minute. Class, in case my voice is clearly audible to all of you, can you all raise your hands? In case my voice and Siddharth's voice are clearly audible to you, please raise your hand. Okay, they are. They are. Great. Yeah, we'll continue, Siddharth. Can you just, for my convenience, once again read out the question? Yeah, and explain it to us basically. What is happening? Yeah. Yes, Siddharth, go ahead.
At a distance of 10 times the radius of the Earth and has a speed of u naught.
Mm-hmm.
And it hits the Earth
Right.
speed v as give. Read out the options.
I I think that there is some issue with the network connection somewhere. So maybe that's why I'm not able to hear Siddharth's voice clearly. No worries. I am telling this question class for everyone's convenience here. Have a look. So we have a planet, right? We have a planet which I have marked in black color. We have an asteroid. The asteroid is approaching the planet, right? Now, initially, it's given that the distance between, the planet and the asteroid is 10 times of RE. So I'll take the, whenever it's given distance no class, we'll take the distance between their centers, right? Whenever it's given that. So let's take the distance as this distance as 10 RE is given, okay? Now the question says, let's say if the initial velocity, when the distance was 10 RE, let's say velocity at that time for the asteroid be u naught, right? Now we are being told that when it hits the Earth, that is when it comes over here, the asteroid comes at the surface of the Earth over here, right? Let's say this was point A, now it comes to point B. With what velocity has it hit the Earth? So this is the point of hitting, right? So it hits the Earth. Now we need to find out what is its velocity at this moment. Let's say its velocity is v. The question says it's v. So we need to find out with what velocity it hits the Earth. What you're going to do, Any idea, Siddharth? We need to find out this velocity v, right? Anything that we had learned in the past classes that can be applied here? Yes, Siddharth.
I'm not sure, sir, to be honest.
Try recalling. Is why is the, just go to the basics. Why is the asteroid coming to Earth?
Because of gravity.
Because of
Because of the
gravity.
Earth's gravity.
And what kind of force is gravity?
It's a conservative force.
Great. If gravity is conservative force, what is conserved?
Mechanical energy.
Mechanical energy is conserved. Absolutely correct. So since mechanical energy
Yes,
is
sir.
conserved, what is this mechanical energy made of? Or what are the two
Sorry,
parts
what?
of the mechanical energy? Yes,
Oh, kinetic and potential.
kinetic and potential. So when we are saying that mechanical energy is conserved, I mean that potential plus kinetic, their sum is conserved, right? That is U plus K is equal
Yes,
to
sir.
constant. Correct, Siddharth? So since it's constant, as
Yes,
the
sir.
planet, as the asteroid travels from A to B, so what will be our equation? Yes, Siddharth. UA plus KA will be equal to UB
Equal
plus KB. Correct?
to UV plus KB. Yes, sir.
This is one of the very simplest principles, dear class, that whenever you have any question which is concerning with the interaction of two heavenly bodies, one is approaching the other, one is moving away from the other, and questions of this sort need to be solved by this approach, because this motion is taking place under the influence of only one strong force, that is gravity. And therefore, in fact, this is not a strong force, this is a weak force. But then just telling you that this kind of interaction is taking place under the influence of gravity. Gravity is a conservative force, and therefore mechanical energy is conserved. Therefore, the sum of U and K is conserved, right? So, how will we go about is, yeah. So, can Karuna, can you help me ahead of this? Yes. How will we calculate the potential energy at the height, sorry, at the distance of 10 RE? Yes, Karuna.
So
Formula for U is minus.
Gm into m by r.
Very good. Okay. So we can write here at A, what is the distance? 10 RE.
At 8, 10 re.
Right.
10 re.
And what is the kinetic energy if the mass is m and velocity is u naught? Half mu naught square, right? And what will be the,
Half mv square.
right?
Yes.
And what will be the potential energy when it reaches the earth, that is at point B?
Minus
Minus.
Gm into m by re.
Sure?
Yes, sir.
Yes, absolutely correct. How about the kinetic energy if the velocity is v and mass is m?
mv square. Half
Half
mv
mv square, right? Half mv square. What do we need to find out in the question? V, right?
v. Yes, sir.
So it's very simple. All you need to do is make half mv square as the subject. So you can uh, reduce or take away m from each side, right? I believe. So you'll have v
Yes, sir.
square is equal to half, or let's take v square by 2 is equal to half u naught square plus gm by re, right? 1 minus 1 by
1 by 10.
10. And then you can take 2 on the other side to give you v square is equal to u naught
U naught
square
square.
plus 2 times of gm by re, 1 minus 1 by 10,
10.
right? So which answer does it match, Karuna, from the given choices? Have a look.
So the last D option, sir.
Option D. Absolutely
Yeah.
correct. Are you clear with the concept now, Karuna? What did we do and why
Yes,
did
sir.
we do it?
Yes, sir.
Sure?
Yes, sir.
Okay. Class, if the approach is clear to all of you, please raise your hand. All we are going to do here is, now that we have the velocity square value, we are going to take root on both sides and get the answer, right? So for getting the answer, take root on both sides and get the answer. Great. It was an easy question, and such questions are very frequently asked in your JEE main exam, right? So gravitation then becomes a very super easy chapter for all of you. And I hope you all are clear with it. Okay, great. All are clear. Karuna, are you clear with this question? Karuna, are you clear with this question? Okay. Now let us move to the next one. Let's take Atul this time. So Atul, can you please read the question for all of us? Yes, Atul. Okay. So, right, class. So, class, we have Atul helping us with this question. Yes, Atul, please read the next question so that we can proceed ahead. Yes, Atul.
Uh, The given figure shows revolution of a planet P around the Sun as if the path traced is elliptical and shaded area SABC is 4 times less or 1/4 of area SLMN.
So, I'll draw this figure here for the convenience of everyone. We have been given that there is some elliptical path. Let's say this is the elliptical path. Now, it's being told that at one of the foci of this elliptical path lies the Sun. Let's say over here we have the Sun. Now we are being told that a planet is revolving around the Sun. A planet, let's say this blue planet, is revolving around the Sun in this given path, right? Now we are given with two different shaded areas. So I'll draw them here. Let's say one is in green in color. So this is the shaded area, right? And we have one more area which is given over here in this manner. Let us make this in another color. So let's take this as pink, right? Something like this. And let me shade this. Now, yes. So get going. Atul, tell us. So we
Yes,
have.
sir.
I'll just do this. So I'll just be naming these points. So this Sun is represented by S. Planet is P. We have points A, B, and point C, right? And then we have points on the periphery of the path N and L, right? So we have this path, and
Yes.
now we are being told, yes, Atul, what is the condition given?
It is given that time taken by the planet to travel from A to B to C is small t, and time taken to travel from N to M to L is capital T.
Absolutely,
And we need to find the ratio between them.
the ratio between the times. Absolutely correct. Anything else? What is given about the area? What is the comment about the area of these uh, shaded zones?
Uh, it is given that the part traced, the shaded area SCBC is 4 times less than the area SLMN.
So 4 times less or 1/4, right?
1/4. Yes,
Right. So
1/4.
let's say if this area is A, this area is capital A. So we are being told that this area A is equal to 1/4 of this capital shaded area A, right? And we are being told now, what's the question? We have to find out the ratio between capital and small t, correct? Right?
Yes, sir.
So how should we go about it, Atul? Any clues?
Uh,
Try recalling
Yes, sir.
the Kepler's law, which we had discussed in yesterday's assignment class, where we were in the end, we had discussed three Kepler's law, right? Let us revise them. What were the Kepler's law?
T
Three
square
laws.
is directly proportional to A cube, sir. I think.
This was third law. Yeah, absolutely correct. That the time period of a planet is direct, if that is represented by T square,
Yes, sir.
directly proportional to R cube. Yes, absolutely correct. T square is directly proportional to R cube or A cube, where R or A is the length of the
Set,
centimeter axis, right?
centimeter axis. Yes, sir.
Right. That is this length. This one. This is R or A, whatever. So if we can name this as A, it becomes A cube. Okay. What next? Yes.
So we will use this formula
So
and substitute the.
this was one. There were two more. First one was that the path traced is elliptical,
Yes, sir.
right? And the
And
second one was that the aerial velocity is constant. What was it? Aerial velocity.
velocity is constant.
What is aerial velocity? Area covered per unit time, right? Delta A by delta T is constant and given by L by 2m,
L by 2 MP.
right? Now it is L by 2m is equal to aerial velocity, or area per unit time is constant. So this means that if the area covered here, have a look, if the area covered in small, if the area covered in small time t for going from A to B to C is small a, and if the area covered to go from N to M to L is in the capital time t, right? So
Yes.
then we have a relation that aerial velocity is constant. We'll write aerial velocity. So we have the solution. Aerial velocity is constant. Aerial velocity is constant implies delta. This implies that delta A upon delta T is a constant, and therefore we have A by capital T is equal to small a by small t, correct? Now I think this will give us the ratio of capital T is to small t will be given as capital A is to small a, and capital A is to small a is nothing but 4 is to 1, right? Have we
Yes,
done
sir.
this, Atul? Right? Are we going correct way, right?
Yes, sir. Yes, sir.
We have the relation between capital and small a. All we had to do is just that, substitute it over here, get the answer, right? Is
Yes,
it
sir.
clear to you?
Yes, sir.
Okay, great. Anybody else, in case you have any queries, just put it forward. And in case everyone is clear, please raise your hand with this question. Yes, class. If you are clear with this question, please raise your hand. All right, Siddharth, do you want to ask something? Yes, Siddharth, go ahead. Tell me. Okay, Siddharth is also clear. Right, class. So thank you. Let us take the next question. Next question tells us question number 5. Okay. Now, what is this question saying us? This question is telling us that we have two masses. Let us take them. We have two bodies. Say this is body number 1, and here is body number 2. We have two bodies and their names are given as A and B. Let's say this is A and this is B. We are being told that there is a point between them, and the point is called as C. Say this is the line joining their centers, and we have a point between them which is C. Right? Now we are being told that if the gravitational intensity, at point C is 0, at point C is 0, then in that case, what is the gravitational potential at that point? Potential at that point. Right? So gravitational potential at C is being asked. Right. So let's restart from Fire. Fire, can you give a try? How will we go about this question? Yes.
I think, is there any information missing in this? Any distance between the
Yeah,
planets?
you can take it up. So let's say we'll give you, let's say this is M1, right? And this is mass as M2. Take the distance between them if you wish to as R. No worries. Yeah, get going now.
Okay, so we can assume the distance between.
I think I have given, maybe I forgotten to write here. The distance between them is given as D in the question.
Oh, okay.
Yeah, the distance between them is given as D. Yeah.
So we can take the distance between M1 and C as X, and the other as D minus X.
Okay, so what Fayed is saying that let us assume that the point C where gravitational intensity is becoming 0. What does that mean first of all? Fayed, can you tell all of us what does gravitational potential becoming 0 at a point mean? Yes.
It means that like if there's a body there, it doesn't get influenced by the other planet, it just stays there.
Right, absolutely correct. So what Fayed is telling us is that whenever we have two bodies with some mass kept at some distance from each other, then there is some point between them where if you keep a body, there'll be no force acting on it. That is, it will experience no force, neither towards the right nor towards the left. C is that point, right? And that point is said to have zero gravitational intensity. Let's say that is at a distance of x from the center of the planet A, and let's say we have that point is at a distance, therefore it will be at a distance d minus x from the center of the planet B. Yes, Siddharth. Yes, Fire. How will we go now? Yeah.
Like we can apply the formula for gravitational field.
Right.
GMM by us.
So we have gravitational field given as G m1, or let's take the force. Let's say this body has a mass m0. So the force on that body on the right, towards the right, because of the body B, will be given as G m1, or sorry, G m0 m2 whole by d minus x square, right? So this is the force acting towards the right because of the body B on the small mass m0. Now the force acting towards left, let's say that force is Fa, and let's say that force is Fa, and that will be given as
Gm0 m1 by
into
x square.
m1 by x square. Absolutely correct. So let's cancel the terms on both sides, m0 and g. What we get is the value of x. How do we get it? Let's take root on both sides. So we'll have m1 by x is equal to m2 root by d minus x, right? So now we can write root m1 into d minus x is equal to root m2. Just correct me anywhere in case you feel that the correction needs to be made. So we have root m1 times x is equal to root m2 times x. Let's take x on one side. So we'll have x given by d under root m1 whole by under root of m1 plus under root of m2, right? Am I correct until here? Fire?
Yes, sir.
Have a look once again. to whatever we did and let me know?
Yes, sir. Correct.
All right. So this is what, this is the distance at which the net gravitational intensity due to both A and B is becoming zero, right? This is that distance. Now, what about the gravitational potential? How will you find out the potential at point C? Yes. It will be the sum of potentials due to A and that due to B,
And B.
right? So let us take that distance. So we have, and also we can find out D minus X here if we wish to. D minus X will be D minus D under root M1 whole by under root M1 plus M2 under root, and this will give us d root m1 plus d root m2. So d root m1 will get cancelled. D root m2 upon root m1 plus root m2.
M2.
Right. So this is the distance of the point C till the point B. So we can, let's say we call it CB or maybe RCB, and let's call this one as RAC. Right. Okay. Now we'll sum the two potentials at point C because of A and because of B to get the answer. We know that potential is given by minus Gm by R, correct? Because of a body M, body of mass M, and at a distance R. This is the value of potential. Yes, Fayed. So how will we go about it? Yeah, tell me. Minus
G
M1
M by
X
yeah,
plus minus Gm2 upon
M2 by
D
D
minus
minus.
X. Correct?
Yes.
Now let's take minus G common. So we'll have M1 by X. Instead of X, we can write D root M1 whole by root M1 plus root M2 plus we have M2 times of under root M1 plus under root M2 whole by D, since this was the second term, so we'll have
D root M.
D under root M2, right?
Yes.
Okay. Now, what will this become? So I think when you sum them up, you'll have minus G and taking root M1 plus root M2 common, you will have them, and also D common from both. We'll have this as root M1 plus root M2. Something like this, right?
No, yes, sir.
Correct, because we can cancel here. If you see class how I've done this, so here in the denominator you have root m1, right? So when you cancel this with the numerator, it will become root m1 over here, because this m2 can also be written as under root of m2 into under root of m2, and one of them will get cancelled. And here I've taken root m1 plus m2 common, and what is left also inside is under root of m1 plus m2. Am I correct in the calculation? Just have a look, Fire.
Yes, sir. Correct.
So we'll get minus G by under root of M1 plus under root of M2 square is the value of potential at point C. Correct? Right? Fire?
Yes, sir.
All right. Great. Class, if this entire approach is clear to all of you, you may raise your hands. But before you do, once again, a quick recap of what we have done. We were given with two bodies, each one with mass M1 and M2. We were told that there is a point between them where gravitational intensity is zero, right? We were told what is the gravitational potential at that point that had to be calculated. So we first found the position of that point by calculating what is the value of X, right? So we calculated what is the value of X here, right? This was that value. Then we also calculated the value D minus X, or the distance of that point from the other planet. So this was X. So we also found what is D minus X. We got these two values, right? Then we found out the potential. Try recalling from yesterday's assignment class that potential is a scalar quantity. So since it is a scalar quantity, we had to just sum the two potentials at point C because of planet A and B. Potential formula is minus Gm by R, where m is the mass of the planet and r is the distance at which the potential is being calculated. We did that and got our final answer, right? So if this approach and everything in the question is clear to you, you may raise your hands. Yes, class. All right. Fayad, you're also clear, right?
Yes, sir.
All right, great. So let's take now the next part of it. Let's Samriddhi be the one who will be answering the questions. All right. Just a second. So now the next question is, yes, Samriddhi, can you read the question for all of us? Yes, go ahead.
There are three particles, each of mass m naught. They
Huh.
are placed at
Huh.
vertices of an equilateral triangle of side L.
All right.
Suppose A and C are fixed, uh, which while B is free to move, find the acceleration of B as it is released.
So I'll repeat the question for everyone's convenience. We have been given a coordinate system XY. We have three masses, each of like three particles, each of mass capital M naught. Okay. Now it says, the question says that these particles are kept on the vertices of an equilateral triangle with length L, and the points have been named as A, B, and C respectively. We are being told that if points A and points C are fixed, that is, you cannot move them, these 2 points are fixed, whereas this point B, or the origin, right, the mass at the origin is free to move. Initially they are kept on the sides of a triangle, now they are free to move. What will happen, or what will be the acceleration of B as it is released? What should be the acceleration of B as it is released when A and C are at their position only? Okay, so can you just give us your approach towards such a question, Samriddhi? Yes, get going. Any idea how should we go about it?
Sir, I could not solve this.
Okay, no worries, no worries. Just try. What you think should be the answer, or maybe anything that comes to your mind on seeing this question. Yeah,
I think, sir, they be attracted with force.
right. So you think that these two masses should attract this given point mass, correct? So let's
Yes,
say this is the force F acting, and the value of force should be same or different, Samriddhi, by both masses.
same.
If the masses are same and the distances are also same, so what do you think? Should we take same force or different force?
Yes, sir, same force
Same force.
because the
Why?
masses and the distance
Distances
will
are
be
same,
same.
right? Correct. Absolutely correct, Samriddhi. So we have the value of force being exerted by the point mass, by these two masses A and C on B will be same. Absolutely correct. Right. Now, once we get this, right? Once we get this, we can find out the force acting first of all. What is the force acting? Can you tell me? And what will this angle be, by the way, Samriddhi? What will these angles be in the equilateral triangle? Each angle will be
60 degree.
60 degree. Absolutely correct. So see, is this not the condition? We have a point B, right? We have two forces which are acting on B, and the forces are at an angle 60 degree from each other. Is it not the condition, Samriddhi, right?
Yes,
Correct. Samriddhi, do you remember the formula of resultant of two forces which are acting at an angle theta, let the forces be A and B. Can you tell what is the formula for resultant? Yes, if the angle between them is theta.
Root of a square plus b square plus 2ab cos theta.
Absolutely correct, Samriddhi. So what are we seeing? We are seeing that if we know that there are two forces, A and B, they are oriented at an angle theta, and the resultant of the two will be a square plus b square plus 2ab cos theta, right? In our case, can you now translate what should be the net force acting because of the two forces along the sides of this triangle? Yes. What should be the net force, Samriddhi? Under root of
F square plus f square plus 2ab cos 60. 2f square
cos 60.
cos 60.
And cos 60 is equal to
1 by 2.
1 by 2. And already there is a 2 over here, right?
Yes.
We'll get f square plus 2 times f square and cos of 60. That is, this 2 and 2 will get cancelled. We have under root of 3f square. Am I correct,
Yes.
Samriddhi?
Yes, sir.
So f will go outside the bracket. We'll have f root 3 is the net force acting. Correct?
Yes,
right?
sir.
Now, if I have net force acting on a block, like on a body of mass, small m naught is F net. So what should be the acceleration? How will you get F net is equal to mass into acceleration?
Mass into acceleration.
Right? This is the net acceleration. So this A net
Yes.
or net acceleration will be then equal to
F net upon m.
M, right? Where what is the mass given in the question? Tell me for that body. M naught. Right? And what did we get the value of F net as?
F by root 3.
F
root 3.
Now, what was F, Samriddhi? In first place, what was F? F is the force which is acting on these individual bodies, right?
Yes, sir.
So the force acting on this body B by body A was F, right? Similarly,
Yes.
F was also the force which was acting on body B because of body C, right,
C.
Samriddhi?
Yes.
Correct. So how can we then write the value of this force by Newton's formula of gravitation? Tell me.
F is equals to G m naught
upon
L square.
L square. Absolutely correct. So we have G m naught
G m
square
naught square
by
upon
L,
L square.
right? By L square.
L square.
Right. Can we substitute it over here then, Samriddhi?
Yes, sir.
Just do
so
it.
A net is equals to
root
G m naught square.
Let's write root 3 by m separately. Let root 3 by m naught. Yeah. Then
G m naught square upon L square.
Right. And we can cancel m naught and m naught square to get acceleration as G m naught by L square.
L square.
Correct?
Yes, sir.
Right, Samriddhi, are we clear with this?
Yes.
Sure.
Yes, sir.
So this is how we have calculated net acceleration. Was it not easy, Samriddhi, right?
Yes, sir.
So your approach was very good, Samriddhi, that we'll consider forces. We know what is the angle between them and will then be easy to find out net force and therefore net acceleration in this given case. Correct, Samriddhi? Are we clear with it?
Yes.
Great, great. So can everyone raise their hands if you're clear with the question? Yes, class. Or in case you have doubt, just let me know so that we can discuss over it. Samriddhi, you are clear, right? Samriddhi, you're clear with the approach, correct, Samriddhi? All right, great. Right. So can we have Karuna with us now? Yes, Karuna. For the next question. Can you read the question, Karuna? Question number 7. Yes, Karuna.
So the question says, plot the graph for gravitational intensity versus distance for a solid sphere of uniform density and hollow spherical shell.
Okay. So,
First subdivision.
Yeah, Karuna, tell me.
So that's the first subdivision.
Right, that's the first. So we have gravitational intensity and gravitational potential being asked for a solid and a hollow sphere, right? So the point is that these questions are although based on derivations, but since in exam we do not have the time of actually deriving such questions, so these should be kept in our mind since this course is a revision course. So class, my suggestion would be that rather than delving very deep into the derivation part of it, for now try to remember this one as a general fact, because these are special cases, and almost every 1 or 2 years or after every 3 to 4 years we have questions popping up from this, either in NEET as well as JEE. That is why I gave this one here, right? Because this concept is very important. Karuna, do you have an idea about it? How do you write it for a solid sphere or a solid planet and a hollow sphere? The value of gravitational intensity and potential. Yes, Karuna, would you like to say something on this? Okay,
No,
all
sir.
right, no worries. So we'll take it up. So just draw, right? Just draw the planet, right? Let's say the planet is represented by this circle here. Now, the gravitational intensity, how does it vary is in this manner. Let's say we are drawing the vertical and the horizontal axis, which are coinciding at the center of the planet. So this is how gravitational intensity varies inside the surface. So I think I'll just do a short change here. I'll maybe draw a hollow sphere here, this way. I think this is a better way to represent it. Okay. Now, when we are talking about a solid sphere, Karuna, what happens is for a solid sphere, the variation of gravitational intensity. And what is gravitational intensity, Karuna, by the way? Can you recall?
So minus Gn by R.
That was potential. That was gravitational potential. Gravitational intensity, Karuna, is nothing but how intense the influence of gravity felt at a point by a unit mass. So we can define it in a similar way we define field. Do you remember the value of gravitational or the understanding of gravitational field? It was force per unit mass, right?
Yes, sir.
So the way we used to write gravitational field is equal to force per unit mass, even gravitational intensity is also the net force acting in value, net force acting per unit mass. So for a uniform solid sphere, so when I'm writing solid sphere, it's actually a uniform solid sphere. That is, its density is constant throughout. So it's a uniform solid sphere, and the way its intensity varies with distance is initially inside this distance r, right? So this r is the radius, right? And initially its intensity is directly proportional. See, it's a straight line, right? And then here onwards it starts in varying inversely. So here intensity is inversely proportional to r square, whereas inside it is directly proportional to r. This is how it goes. Is the point clear, Karuna?
Yes, sir.
Would you be able to remember it that inside it's a direct variation, whereas outside it's a variation in the form of a inverse square root, right?
Yes, sir.
Just the way the force varies, right? Because we know that we just told that gravitational intensity is nothing but force being experienced per unit mass, right? So since force varies inversely outside the body, and therefore we have this 1 by r square relation, right? Are we clear on this, Karuna?
Yes, sir.
And how about the gravitational intensity inside a hollow sphere? Try recalling from yesterday's class on gravitation. Do we have any influence on a body? Let's say the body is inside this hollow sphere. Does it have any feeling of the gravitational force when it is on inside a hollow sphere, Karuna? From yesterday's class, just recall. Whenever a body is inside a hollow sphere, will it feel gravity?
No, sir.
No, right? Whereas whenever it is inside a solid sphere, it will feel gravity only because of the part which is inside it, right? Do you
Yes.
remember this one, this part, Karuna? Right?
Yes, sir. Yes.
That whatever part is below or inside this will only be able to make gravity influential on this point mass m. And since here inside this hollow sphere there is no mass below this object or small mass m naught, there is no mass over here, there is nothing over here, so there is no gravity or no influence of gravity inside the hollow sphere. Therefore gravitational intensity should be 0.
0.
Right? Are we clear on this, Karuna?
Yes, sir.
All right, so I'll just remove these additional diagrams. Acha, what about the outside variation? Do you remember what will happen? What will be the influence of the hollow sphere on a mass which is outside it?
So it will be
It
inversely
will be
proportional to r square.
absolutely correct. It will be inversely proportional to r square. So it will behave as a point object. Do you remember? It will behave
Yes, sir.
as a point object, right?
Object.
So inside it, gravitational intensity will be 0. So I intensity will be 0 inside a hollow sphere, whereas outside it, it will be inversely proportional to r square, right? Are we clear on this, Karuna?
Yes, sir.
Right? And this is nothing but the distance r, right? This is the distance r. So now let us move ahead. Let us proceed ahead. So we'll write here. So this was basically for gravitational intensity. Now let's take gravitational potential. So potential is given by minus gm by r for a point mass, right? For a point mass. So it's easy to draw this for I'll take the color. Okay. Let's keep this solid sphere here. Then hollow spherical shell. Then we will have their horizontal and vertical axis given in this pattern. So in case you have read a chapter called as electrostatics in class 12, there you will also read about potential, right, Karuna?
Yes, sir.
So we read in gravitational potential, the chapter gravitational potential, that there is this variation of potential inside the sphere or inside a hollow and spherical sphere. So the point is, whenever the sphere is hollow, I will repeat, whenever the sphere is hollow, the potential inside will not vary. This is the case with a hollow sphere. Same thing holds here, Karuna. Same thing holds here. So here also, inside a hollow sphere, potential remains constant. Potential remains constant, right?
Constant.
So when I'm talking about gravitational potential, it is constant inside a sphere. So it is constant the way I've shown. And then, so or maybe I'll draw this over here. So just a second. A better way is I'll rub this one, or maybe I'll draw it upwards like this, just to denote what is r, how much is the r distance, and just I'll show the, so shifting this up just to show that this is r, this is r. And now I want to show how is the gravitational potential varying. Tell me one thing, Karuna, should it be negative or should it be positive? Just have a look at the formula.
Negative, sir.
Negative, right? So since it's negative inside the sphere, right? Until the distance r, it's negative, and then outside it, negative and constant, and then it starts varying inversely with the distance r. So inside the hollow sphere, the potential is constant and negative, given by the same value as that on the surface. And then it starts varying inversely V is inversely proportional to R. Outside it, we are plotting a graph between gravitational potential and distance for a hollow sphere. For a hollow sphere. I'll repeat, for a hollow sphere, inside the sphere, the gravitational potential is constant and same as that on the surface throughout. Wherever you find out the gravitational potential, it will be always of the same value as that on the surface, whereas it will vary for the uh, distance outside, right? Now, let us take this one for a solid sphere. So for a solid sphere, the funda is very unique. So let's draw it this time over here. I'll cut this line. So let's say this is the line, okay? Now, how does it vary? Let's say this is the distance r. This is the distance r, right? Now, how does it vary? So the point is basically inside the uniform solid sphere, inside the uniform solid sphere, the variation is parabolic. This way. The variation is parabolic. This is a parabolic graph. And then outside it, it's a hyperbolic graph this way. This is hyperbolic, right? And these values at the surface and at the center for gravitational potential. I will repeat, the value of gravitational potential at the surface and at the center. So this is the center, that is r is equal to 0, right? Whereas this is the surface, r is equal to r. So at these places, the values of potential are given as, so at the surface, if it is equal to minus gm by r, same as before, at the center, it is minus 3 by 2 gm by r. That means the potential at the center is 3 by 2 times of potential at the surface. And what is that potential at the surface? Minus gm by r. Minus gm by r. Same as that in the hollow sphere, right? Just that in the hollow sphere, inside the potential remains same. Whereas for a solid sphere, uniform solid sphere, it changes in the parabolic fashion. So this was a parabolic curve. Inside the sphere, it changes on a parabolic pattern this way, right? And becomes 3 by 2 times of its value on the surface, right? So it increases in magnitude. Its magnitude increases, although its net value is decreasing, but its magnitude increases, right? And it becomes 3 by 2 of its value at the surface. It's gm by r. So this is gm by r, right? So am I clear on this, Karuna? Whatever I've said on the screen, is it clear?
Yes, sir. Yes,
okay. So can you repeat all of this for everybody's convenience here? Whatever I've said, the 4 points. Yes, Karuna, get going.
The graph between gravitational intensity and the distance for solid sphere. Inside the sphere, it's directly proportional to r, and outside it's inversely proportional to the square of r. For hollow sphere, inside the gravitational intensity is 0. Outside it's directly proportional to 1 by r square, inversely proportional to r square.
Right. Outside it's inversely proportional to 1 by r square. Yes. Yes. What next?
For gravitational potential, for solid sphere, it's inside it's parabolic and outside it becomes hyperbolic. And for hollow sphere, inside
and what is another important point to be noted here? What's the next point to be noted here?
That VC is 3 by 2 of VS.
What is VC and VS?
VC is the center potential and gravitational potential at center, and VS is at surface.
Right, absolutely correct. How about a hollow sphere? Variation of gravitational potential in a hollow sphere?
Inside it's constant, and outside it becomes inversely proportional to r.
Absolutely correct. Absolutely correct. So thank you for this revision. Class, are these 4 points clear to all of you? If yes, please raise your hand. Yes, class. Samriddhi, is it clear to you, Bacha?
Yes, sir.
Clear, right? Okay, great, great. Thank you, class. Let us take the next one. So let us have Atul with us now. Okay, okay. So Atul, can you read the next question for all of us? Question number 8.
Yes, sir. If a man weighs 100 Newton on the surface of Earth, find man's weight on at a distance r by 2 from Earth's center. Re is the radius of Earth.
So we have Earth being given. Let's say this is the Earth given, right? What are we being told? We are being told that in the question that at the surface, if a man has weight equal to
100 Newton.
100 Newton, what will happen to the weight as we go below into the Earth's surface at what point?
R by 2
R by 2 from where?
from the center of the Earth.
From the center of the Earth. Very important. So sometimes what happens is they will tell you distance from the surface. Other times they'll tell you distance from the center of the Earth. So you all have to be very vigilant or very aware on what is the question asking, right? That is important. So here they are saying at a distance of r by 2 from the center. We are being told what will be the weight of the man. So here, so let's say point A. At point A, weight is 100 Newton. We are being told to find out what will be the weight at point B, where this is B, and O is the center. Okay, any approach that comes to your mind, Atul?
So first we will find the mass of the man at the surface of the Earth.
Mm-hmm.
Then we will find G, small g at a point at a point
Uh-huh.
r by 2 from the center
Uh-huh.
of the Earth.
Uh-huh.
That
Right.
yes, sir.
Right.
Then
Yeah. Tell me. That's the way, right? Great. So let us do
yes,
this one thing. We know that weight is equal to m into g, correct? So we
yes, sir.
can write weight at A is equal to m into GA, right? And similarly, weight at B is equal to m into GB. You can write it this way, correct? Do we have a direct formula which connects the depth of, like connects the gravity
Yes, sir.
variation with depth?
Yes, sir.
It is given as uh,
GD
GD is
equals to
equal to
GS
G
GS
times
into
of 1
1
minus
minus by R.
T by R. Very good, very good. So now we can write GD by G, right? So gravity uh, or acceleration due to gravity at depth GD upon acceleration due to gravity at the surface, which is GS or G, is equal to 1 minus depth by R, correct?
Yes, sir.
Now, what is the value of, what have we denoted these values as GB and GA, right? GB is
GA.
acceleration due to gravity inside, and GA is acceleration due to gravity on the surface, correct?
Yes, sir.
We have this as RE by 2, and this whole is
2
RE. So
R.
it's 1 by 2, right? And therefore, when we multiply M in the numerator and denominator, we'll have MGB whole by MGA is equal
GA.
to 1 by 2, correct?
Yes, sir.
And therefore, this becomes weight B upon weight A is equal to, or weight at point B upon weight at point A is equal to 1 by 2, correct? Now, this should yield us weight at point B is equal to weight at point A whole by 2, correct? And therefore, we should have the answer as 100 by 2 or 50 newtons. Easy? Atul, clear? So, Atul, is this clear to you? I think there is some network issue at Atul's end. No worries, you can put me a message on chat box. No worries. How about all the others? Payat, Karuna, Samriddhi, is the question and the approach clear? Siddharth,
So
everyone?
am I audible now?
Yeah, Atul, you're audible now. Is it clear to you, Atul? Is the approach
Yes,
and the
sir.
question clear to you?
Yes, sir.
Okay, great, very good. All right. So now let us take Siddharth. Siddharth, let us take question number 9. Can you read it for all of us? Yes, Siddharth.
Yes, sir.
Yeah.
So, question number 9.
Uh-huh.
I'm sorry, I'm just getting the assignment open again because I have to switch between this and the Zoom window. So,
That's okay.
um, so question number 9 says a ball is projected from Earth with speed 3 VE.
Mm-hmm. So
Find
we
the
have,
height,
yeah.
the escape velocity, 3 times the escape velocity. So find the height attained by it finally.
So we are being told that there is a planet from the surface of which we have projected a ball upwards with a velocity which is 3 times VE or 3 times the escape velocity.
Escape velocity.
What is meant by escape velocity?
It's the minimum velocity required to,
Uh,
escape the Earth's atmosphere.
right. So
Gravitation pull.
not the atmosphere, but yeah, but the Earth's gravitational field. So if you have to
Yes, sir.
escape the gravitational field of a planet, you need to give a bare minimum velocity to that object, and that is told as escape velocity. What is its value, Siddharth? Do you know? VE is equal to under root of
I don't know, sir.
2 gm by r. VE is equal to under root of 2 gm by r. So this was one of the formulas, Siddharth, which we had again discussed yesterday. I would once again suggest, please do make sure that you remember such small formulas because they're going to become very handy when you solve questions, right?
Yes.
Okay. So what is the escape velocity, Siddharth? What is it given as? Under root of
2 gm by r.
2 gm by r. Okay. Now let
projected velocity is 3 times
3 times this velocity, right?
Yes,
suppose this is the radius r. Let us assume that it reaches the height h. It reaches the height h from the surface of the earth, right? It reaches the height h from the surface of the earth. Now tell me one thing, Siddharth. So if this body goes from the surface and we are being told that it reaches the height h, what does this mean? Reaches the height h means that is the maximum height to which that body can go. Correct?
Yes, sir.
What happens at the maximum height? Does the body stop moving? Does it continue moving upwards, or just turns right, turns left, comes back? What happens?
So the velocity, it first reaches 0 and then it goes back to the ground if it had not escaped the gravitational field.
Yes. So since it is 3 times VE, so we know that it has to definitely escape the gravitational field, right?
Yes,
now as it goes away to a very large height, what happens is over here at some point when it stops,
it will just stop
what
moving.
will be its kinetic energy? First of all, if it stops momentarily at this point, zero, because the velocity is becoming 0. It will definitely have some potential energy. Let's say this is point P. The value of KB and will be 0, but we'll have some value of UB, which will depend upon the distance from the center. Correct?
Yes, sir.
How about let's say this is the point from where it started on the surface as point A. How about the potential energy and kinetic energy here? We'll also have some values of that over here, right?
Potential will be 0 and kinetic energy will be based on the mass, right?
Are you sure potential will be 0 at the surface of the earth with respect to the center?
Yes, because the height is 0. Oh no, wait, it will be radius times mg. So mgr. No.
No worries, but try recalling. What's the formula? So what you're saying, Siddharth, is correct, but it is correct when you take. So just 1 minute, right? Have a look at this.
Yes,
let's say you have a ball which is kept on the floor. You are right to say when you say that the potential energy of the ball is 0 with respect to the floor. But this floor is, if this floor is a part, we consider this floor as a part of the big earth, right? And let's say this floor is at a distance r from the earth. Now no longer is the potential energy of the ball 0. Now also the ball will have some potential energy. I can prove this to you. Suppose you put this ball in a well, in a
Yes,
well.
sir.
Will it gain some velocity or not as it is going down?
It will, sir.
It will. So it
Yeah.
when it gains some velocity as it is going down the well, it means it has some kinetic energy. Correct?
Yes, sir.
Where did this energy come from? It
From the
came
potential
from
energy.
this potential energy. Yes.
Yeah.
Yes. So this is how we are trying to say that whenever a ball is kept on the floor, that ball has zero potential energy taking the floor into reference and non-zero potential energy taking the center of the earth into the reference. Are we clear
Oh
on this,
yeah, it'll
Siddharth?
be. Yes, sir. It'll be
And
minus
that,
GMM by R. I just
yes, and
understood that.
that potential energy is given by minus GMM by R. Are we
Yes,
clear
sir.
on this, Siddharth?
Yes, sir.
Okay. So we have potential energy, and what will be the approach? Now, you know everything. We know that there'll be some potential energy at point A.
Yes, sir.
There'll be some kinetic energy because the body has a velocity 3v. It goes
Yes,
until
sir.
the height B momentarily stops there, either to return back or to not return back. That is a very different scenario. But right
Yes,
now,
sir.
what are we concerned in the question with? We have to find out until what height does the ball go. That is the height at which the kinetic energy becomes zero, right? We need to find that height h. Okay, so what should be the approach? And yeah, get going.
So we have expressions for potential and kinetic energy uh, in terms of G, mass of the Earth, the mass of the ball, and R.
Okay, so what?
I mean the distance. So when if we substitute for all this,
Where
probably
where do we need to substitute all this?
can we assume that the energy is conserved?
Which energy?
The potential energy and the kinetic energy. I mean the same way we did it for mechanical energy in previous questions.
Yes, so what energy is conserved? Mechanical energy is conserved. Why should it be
Yes, sir.
conserved?
Because gravity is a conservative force.
Because the motion of the object is taking place under the influence of
Influence
gravitational
of
force,
gravity.
right?
Right.
And gravity is a conservative force, therefore mechanical energy is conserved. Simple,
Is conserved. Yes, sir.
right? Okay, so therefore we'll write net mechanical energy, or U plus K, is conserved or constant, and therefore we can write put sum of potential energy
At
and
A
kinetic
and
energy
kinetic
at
energy
A
at A
is equal to
equal
sum
to
of potential energy and kinetic energy
kinetic
at B.
energy at B
Therefore, we'll have minus GMM upon R
by
is the
R.
potential energy at point A, because the distance from the center of the earth is A, plus half
GMM by 2R.
mv square. Let us take this as half mv square. What you are
Okay.
taking, Siddharth, is the kinetic energy of a satellite. But is this a satellite? No.
Oh,
This is
not yet.
just a projectile, right? So
Yes,
this
sir.
is the point of caution. You will not take kinetic energy as GMM by 2R,
GMM by
because that
2R.
is the energy of a satellite which is revolving very close to the earth. So we'll not take
Earth.
that, right? Because this might make you end up in a wrong answer, right? So yeah,
Yes, sir.
let's avoid that. Now for now, we'll take this as half mv
Half
square,
MV squared.
right? And
And that V is 3 times VE.
yes. So had you
Okay.
taken my that GMM by 2R as kinetic energy, you would definitely get a wrong answer. Now we know,
Right, because we don't have
right?
anything to
Now we know,
substitute for.
because this
Yeah.
V would be 3 times of VE, correct? Okay.
Yeah.
Now what about the potential energy at point B? Tell me.
It's going to be whatever height it reached plus R
Minus GMM by H plus R
by H plus R. Yeah.
plus half mv square. Should we include this?
So the kinetic energy at that point is 0.
So this will be 0. Now let's substitute the values. We have minus GMM
G
upon
by
R
R
plus M
plus
by 2
R
into what
by
will be
M.
the value of V square? V
3.
is
So
equal,
9 VE squared.
yes, V is equal to 3 VE. So V square is equal to 9 VE square. And what is the value of VE? Under root of 2
Uh,
GM by R,
yeah. So we can just
right?
take it as 2 GM by R. So
Yes.
18 GM by R.
So let us write it even clearly. We have to write the value of velocity at the surface of Earth, which is 3 times of VE, which is, and the square will yield us,
Um,
the square will give us V square is equal to 9VE square, and therefore we have 9 times of, instead of VE square, we'll have 2 GM by
2
R,
gm by r,
and this will give us 18
18
GM.
gm by r.
Now we'll substitute 18 GM by R over here. This is equal to minus GMM by R plus H plus 0. Now,
So we can
once we have this,
cancel
yes,
capital M and small m.
yes, so we can cancel the common terms on both sides. Let us do that.
And 2 and 18.
We'll have G, G getting cancelled, capital M on all sides getting cancelled. Also, I think small m is on
Small m also gets
this
cancelled, yeah.
side, on all get cancelled. Now let's write the
So
remaining.
18 by 2 becomes 9.
Right. So we have minus 1 by R
1 by r
plus 9 by R is equal to 1 by
equals
R
9.
plus H. Am I correct in writing this? Have a look.
So the minus sign
Yeah.
on the
Yeah.
RHS.
Great.
Yeah.
Okay. So now, class, we have this as the resulting equation. Let us proceed to the answer.
We can take r to the other side and we get 10 equals
Yes, let's rearrange
RHS.
and play a little with mathematics. Now, class, after this is just a simple play of algebra. We'll have 1 minus 1 by R plus 9 by R is equal to minus 1 by R plus H, minus 1 by R plus H.
H.
And therefore, this will become 8 by R is equal to minus 1 by R plus H. And so this will become 8R plus 8H is equal to minus R.
R.
And what will our equation look like? Let us see. Just have a look. Have we gone wrong somewhere in calculations? Just have a look. Minus J1 by square. Fire. Yes, fire. Tell me.
Sir, this is theoretically impossible, right? Because if we give something more velocity than escape velocity, it will like go on to like infinity, right? Without
Yes.
stopping.
Yes. Yes. So we'll see what our answer comes out to be first. Let's try to reach the answer. So we are being told that it will go to some height. Let's say we want to find out that height. We are determined on finding it. So we get 8h is equal to minus r minus 8r, and therefore h coming out to be minus 9r by 8, which is an impossible answer. So when you were given this question, when I was given this question, I'll have 4 options. Some random values,
Right.
of course. Let's say we have one value is 9r by 8, one value is 2r, and one value is r. The next one is not possible, right? And
Right.
fire will tell us that y is not possible, one of the correct options. Yes, fire, tell us.
Yes, sir. For escaping the gravitational field, we have to give v velocity to the object.
Right, right.
So if we give like even a small amount more than that, it means like there is nothing to stop the body or bring it back. So it will go till infinity.
Uh-huh. Uh-huh. Absolutely. So the point is escape velocity, as we had just discussed, helps a body to reach the interstellar space where the body is very, very far away from the planet. So it automatically means that there it is at a distance which is very, very large or infinitely large, right? Now to make that happen, if we take the value of escape velocity much higher, or value of velocity much higher than escape velocity, then definitely it is going into the interstellar space. So let's say if this is the Earth, from here we projected a body at escape velocity. where it reaches, it is infinity. Now, if we take a velocity 3 times of escape velocity, it is definitely going into the interstellar space, right? So one of the options, instead of writing not possible, might give you interstellar space. Interstellar. Is my point clear, everyone? That if the velocity of the object or the projectile from the earth is equal to escape velocity, then the entire projectile goes into the interstellar space, which is at a distance infinite. That is, interstellar space means something which is at an infinite distance from the body, such that from the planet, such that the gravitational field's influence vanishes at this point. Here, there should be no gravity because of this planet. This zone is called as interstellar space. Now, if you increase the velocity from VE to 3E, 3VE, it is definitely going to reach there. Let's take a more feasible case, right? Let's take a more feasible case. Now, let's say we have again a planet, right? Again a body is projected from here, but this time with a velocity which is half of the escape velocity. Now let us say the velocity is VE by 2. Now let's see what will happen and until what height will this object reach. Let us say it reaches until a height of h, and let's say this distance from the center is r, right? So of this surface, so on an obvious note, we are going to have, just a second class, yeah, so we are going to have, let's say this is point A again, this is point B again. We are saying that a body is projected with an initial velocity VE by 2, right, from point A. We have to find out what is the height until which it is going to reach. So again, it is moving under the influence of a conservative force. Therefore, the net energy is conserved. What energy? Mechanical energy is conserved, and therefore we have UA plus KA is equal to UB plus KB. Therefore, we will have, again, we are assuming that it goes here at point B and stops. So kinetic energy at point B is 0 because the body is stopping there. Now, potential energy of the body at point A is minus G mm upon R. Kinetic energy is half m v square. Let's say its velocity was equal to v, which is VE by 2. We'll substitute in the next step. And at point B, its potential energy is UV. So minus GMM, the distance from the center of the earth is 1 by, is h by h plus r. All you have to do is now substitute again minus GMM by r plus half m. Instead of v, we're going to write VE by 2, right? Therefore, V square is equal VE to VE square by 4. That is 2 GM by r whole by 4. That is GM by 2r. So we have G into M by 2 into R is equal to minus GMM by R plus H by R plus H. Let's cancel out the common terms, GMM, GMM, and GMM from all sides. This giving us minus 1 by R is equal to, or let's minus 1 by R plus 1 by 4R is equal to 1 by H plus R. So we have the equation given as minus 3 by 4R minus 3 by 4R is equal to minus 3 by 4R is equal to minus 1 by H plus R. Therefore, 3 by 4R is equal to 1 by H plus R. Therefore, 3H plus 3R is equal to 4R. And so we have 3H is equal to R and h is equal to r by 3. It means that if you project a body with velocity, so I'm drawing three cases here, class. We're drawing three cases here. If a body is projected with an angle, with a velocity ve, then it is obviously going into reach, or it is obviously going to reach the interstellar space, that is at a very, very large height equal to infinity. If it is obviously then, let's say, projected with even higher speed, let's say 3ve, again it's very obvious that it is definitely again going into the interstellar space, right, where r is infinity. But if it is projected with a velocity which is lesser than the escape velocity, or let's say in our case we had taken it as ve by 2, half of escape velocity, then we realize that this h, or the height to which it reaches, is r by 3. So it's 1/3 of the radius. So if you would want to geometrically see this, so let's say if this is the radius r, if this is the radius r, then this body is going to reach over here until r by 3. So over here, maybe if this is r by 3, this is going to be the height until which the body travels and stops. Then it is again going to come down. So these are the three cases, class. One, case A, where, or let me name them as case 1, when the body is projected with VE or escape velocity. Here the body is projected with 3 VE. In both cases it goes into the interstellar space, whereas when it is projected with a velocity VE by 2, we are getting that it reaches the height r by 3. Suppose if I ask, Siddharth, let me know if you can answer this. Suppose that I ask that what is the new distance between the body and the center of the earth? Yes, quick. R plus r by 3. That is 4r by 3, correct?
Right.
So I'm asking, what is the new distance between that point where the object has reached and the center of the earth? But obvious, this is h plus r, and therefore r is, we know that h is r by 3. So r plus r by 3 is giving you 4r by
3.
This is the new distance between this point where the object has reached, this mass has reached, and the center of the planet, right?
Right.
Are we clear with this, Siddharth and everybody in the class? Just so we have all of you as Fayad, Karuna, right? Atul, Siddharth, Samriddhi. Are you all clear? If yes, please raise your hands. Yes, class. Okay, great, great. So class, just have a look one by one. I'll go through all the slides from where we went through in the session, right? In case you have any queries in any of these, you may let me know. Yeah. Yes, class. Anybody, any queries may raise their hands. The rest may put their hands down. Yes, class. Any queries, anyone? Okay, great. So thank you everyone for attending this session of a session where we had some discussions, right? Where we had some discussions of understanding different concepts. So thank you everyone. Thanks a lot for being a part of the session. Thank you. Thank you so much, class.